This is G.Smart saying g'day from New Zealand. We'll start the talk by looking at some of the theory behind the alpha ratio equations, and we'll look at the situations where alpha ratio may vary. We'll end up with a summary visually presented. We have here the Pararoa River on the west coast of the South Island of New Zealand, and I wonder what the alpha ratio might be in this river. We're getting a lot of new technologies for measuring water surface velocity, but how good are our methods of converting this surface velocity to mean velocity using an alpha coefficient? Title of the talk really means, are changes in alpha significant, or is this alpha just a superficial coefficient? Superficial means related to the surface, but it also means appearing to be true or real only until examined more closely. And in this talk, we're going to examine alpha more closely. We're looking here at the Pukeroa River in Southland at the bottom of the South Island of New Zealand. And I wonder what the alpha ratio is here. Well, here we see a profile of velocity, and to get the true depth averaged velocity, what we have to do, as the name says, is average it over the depth. If we have an equation for the profile, such as with a log law, we can mathematically integrate it and get the depth averaged velocity. If we have Manning's equation, it already gives the depth averaged mean velocity, and if we substitute the slope in Manning's equation with the shear stress equation, we can write Manning's equation as a power law in a similar way to the log law. From our profile equations, we can calculate the surface velocity. So with the log law, we just substitute h for z in the log law, and this then gives us our surface velocity. Similarly with Manning's profile, this is the equation which when integrated will give Manning's equation. We substitute again for h and we get a surface velocity. So we can now get a theoretical alpha value by dividing the mean velocity equation by the surface velocity equation. And you'll all know that the USGS recommends a value of 0.85. With the log law equation, we get this relatively simple alpha formula, and you can see that the alpha ratio here depends on the surface velocity and depends on the shear stress. With Manning's equation, everything cancels out and we just get 6/7 for the mean velocity to surface velocity, giving an alpha ratio of 0.85, which is the same as the recommended USGS value. So things are looking good. But is this superficial? Here we've got the Ruamahanga River in the south part of the North Island of New Zealand, and I wonder what the alpha ratio is here. So when we check the field data, we sometimes find that the profile looks nothing like a log profile, and in fact when we have a very rough bed, we often get something more like a linear profile of velocity with depth. So let's now look more closely at some of the field data. So we're looking here at data from over 100 New Zealand rivers, and we're plotting the mean velocity scaled by shear velocity against the relative depth. That's the depth in relation to a grain size of the bed. And these are the parameters that are used in the equations that we saw earlier. Now we've fitted to this data trend lines, and these trend lines are fitted for different relative depth ranges, and we've fitted them as a power law. And if we consider the exponent of the power law as m, we can see that this exponent gets smaller as the depth gets bigger, until at deep relative depths we're approaching the 1/6 value that the Manning's equation has. So our exponent depends on the relative depth. If we take our generic power law equation and do the same thing as before and divide the mean velocity by the surface velocity, we get an equation for alpha that only depends on m, the exponent of the power law. You recall for Manning's equation as a power law, we had a 1/6 exponent, and this gives an alpha of 0.86, which is what we would expect. Now, if we go back to the data from our last graph, we had a range of relative depths, and these had a range of exponents that were appropriate. And by substituting these exponents into this equation here, we can predict what alpha values are applicable to these relative depth ranges. And you can see that for relatively deep flows, we get our conventional alpha values, but when we get down to the very shallow depths, we have alpha values that wouldn't typically be used in practice. We can look at more complicated composite profiles. We won't go into this in a lot of detail, but you can see mathematically we can still, for these, calculate equations for the alpha ratio, where the linear region or where there's a linear region with a log region on the top, and get estimates of what alpha should be. We can also look, we've got the Waimangaroa River here in Northwestland. We can also look what happens where the bed is permeable. So some of the flow is passing through the bed, and this affects our alpha ratio. And in order to do this, we assume there's an overlying log law, and the flow penetrates a distance p from the origin of the log law. So the velocity goes to 0 within the bed itself. And we, using this, can also calculate what happens to the alpha ratio as this penetration distance changes relative to the overall flow depth. And it's a little bit complicated, depends on the roughness as well as the penetration depth. What you can see is that only at the 0 permeability of bed cases do we get our conventional alpha ratios, and as this penetration or the permeability of the bed increases, so our alpha ratio drops. Then we come to the effect of surface wind and surface waves and how these change the alpha ratio. And this started to get quite complicated because there's an interaction of factors. The best way to understand this is to look at it graphically. And so now we're going to enter our virtual river simulator and show what some of the equations we've just talked about predict. So here we are looking at our simulator, a river simulator. We take the depth up to a meter, and essentially we've just got a pond here. There's no slope on the channel. If the wind blows upstream, we'll get a velocity profile of water going upstream at the surface and 0 at the bed, or if the wind blows downstream, we'll get same thing in the downstream direction. And then if we are to increase the shear stress on the flow, this is like by tilting the channel bed so that we get a gradient, a downslope component of gravity, we then get our typical velocity profile. At the surface, we've got what we measure from our remote sensing, and then we've also got our depth integrated average, and we've got our alpha ratio of those two. And in this case, it's 0.86 for the values of roughness and depth that we're using shear stress. When we change the shear stress, the alpha ratio stays the same. It affects both the surface velocity and the mean velocity in the same way. So changing shear stress doesn't change the alpha ratio. This is important. However, if we change the roughness now, you see the bed's getting rougher. As we make it rougher, we'll increase the shear stress. Make it more rough on the bed. You can see that our alpha ratio is dropping. Now it's not major, but it is reducing. If we make it even rougher on the bed though, it becomes more serious. The shear stress will increase even more, and we're down to about a 0.6 for alpha, which is significantly different from the conventional value. Now we'll look at what happens with permeable bed. So this is when some of the flow is going through the bed, and you can see here that the alpha drops further, taking the permeability up and down. You can see how alpha increases or decreases, and the whole velocity profile is slightly shifted. So then, next thing we're going to do is we'll take our roughnesses back to standard typical river type values, and we're going to have a look at what happens if there's wind starting to blow on the surface. So if the wind's blowing upstream, as we saw before, we get an upstream component of velocity near the surface, and this is now on top of the downstream velocity profile, so we get this curved shape. But you see what happens to alpha. It suffers an enormous change because the surface velocity is not indicative. And as the shear stress on the wind picks up, the water surface is going to get rough. We're going to have waves form, which will then increase the shear stress even further on the surface. And you can see how we can get very high alpha ratios under these circumstances. In fact, if the wind is strong enough, we can have the negative velocities at the very surface, yet still have a positive mean velocity, which will give us a negative alpha ratio of 2.4, which is incredible. Similarly, a downstream velocity reduces alpha, and we have the same thing in the other direction, but it is affected by that. So now we've sort of covered the range. We'll pull the plug on the depth and let the water go. We've had a lot of trouble with fish in these experiments getting lodged in our equipment. So thank you for your attention, and we'll get back to the normal talk. We see here a river which seems to have been named in honor of the workshop that we're having. We'll just wind up now by summarizing what we found throughout the talk. So we looked at the theory behind alpha values, and we found that both the theory and the measurements indicate alpha can deviate markedly from standard values when there's high bed roughness, bed permeability, or surface wind. So to answer the topic, the title of the talk, alpha's definitely not uniform, Charlie. Thank you. That's it. Sorry that I couldn't be with you at the workshop. Maybe next year, or maybe you can come down to New Zealand and inspect some of our rivers from above. Thank you very much for your attention. Looking forward to future collaboration. Goodbye from New Zealand.